Hello, I'm Bretton, one of our MCAT tutors here at Inspire Advantage, where we help students get accepted into medical schools and other professional programs. Welcome back to MCAT Bites. Today, we're sinking our teeth deeper into the world of alkenes. These molecules are not just the cornerstone of organic chemistry, but also incredibly important for the Chem Phys section of the MCAT. Let's zoom in onto the mechanistics of two key types of reactions, addition and epoxidation. Just like with math early on in your career, we'll start with addition. Addition reactions are the heart of alkene chemistry. Let's take hydrogen halide addition as an example. When a molecule like hydrogen bromide, HBr, adds to an alkene, it doesn't just slap on haphazardly. The reaction follows a precise sequence of steps. Initially, the pi electrons from the double bond are attracted to the partially positive hydrogen of HBr. Then, the double bond will break, and the electrons will move to form a bond with the hydrogen, generating a carbocation intermediate. Carbocation sounds like a scary word, but really it's just a carbon with a positive charge. This positively charged intermediate is the key player in this reaction. It's highly reactive and will readily bind to the bromide ion that was left in the wake of the hydrogen. But not just any carbocation will do. The reaction favors forming the most stable carbocation, which is typically the more substituted one, a concept explained by Markovnikov's rule. This rule, which says the rich get richer, the hydrogenes get more hydrogenated, guides us in predicting the major product of such addition reactions. Let's take a look at an example problem here. Imagine ethylene is reacting with hydrochloric acid. The pi bond attacks the hydrogen, forming a carbocation. Where then is the chlorine going to attach? Take a few moments to think this one through. So we have our ethylene and our acid here. So first, the hydrogen is going to come on over, being grabbed by one of those double bonds. Then we're going to have this molecule here. We're going to find our carbocation, intermediate. It's this guy, it's our positively charged carbon. And now our chlorine, which is negatively charged, it's going to be attracted to this. So it's going to bind on in, and then boom, we've got our chlorine attached. Notice we no longer have our double bond. Hydrogenation is all about turning alkenes into alkanes. That means there's no double bond. This reduction requires a metal catalyst like platinum, palladium, or nickel. The alkene approaches the catalyst surface, and the pi bond weakens as the electrons interact with the metal. Hydrogen molecules absorb on the catalyst to dissociate into atoms and add to the carbons of the alkene from the same side, leading to syn addition, SYN. This means that new hydrogens end up on the same face of the double bond, maintaining the stereochemistry. We can see an example of this here. Notice we have our alkene coming down to a metal. Let's say this is platinum because we're bougie. It's going to go down bind, and we see that the hydrogens are all on the same side because it has to, because this is where it's interacting with the metal. This is syn addition. SYN. Switching gears ever so slightly, let's take a look at epoxidation. And this kind of tells you what's going on. So epoxide is this little guy. It's the triangle. We've got an oxygen and two carbons forming an epoxidation. So just making epoxides. So the reaction that makes epoxides. This reaction specifically will transform an alkene into an epoxide, a three-membered oxygen-containing ring. Here's how it unfolds. The alkene's pi electrons act as a nucleophile, attacking the electrophilic oxygen. This mechanism results in the formation of an oxyrane ring, with the oxygen inserted between the two carbons of the original double bond. This reaction is stereospecific, preserving the geometry of the starting alkene in the epoxide product. What this means is that if it was R before, it's R now. Let's take another look. Say we've got a simple cyclohexane with a double bond here. We stick this carboxylic acid group and a chlorine, we're going to try and form that into an epoxide. So how is this going to happen? Well, the alkene's pi electrons over here are going to act as a nucleophile and attack the oxygen. It's going to look something like this, where the electrons from the double bond are both going to attack on opposite carbons, causing a new bond to form. So it's going to be from over this carbon and this carbon, we're going to rejoin the oxygen, kind of like this. Now let's do an example problem. Propene reacts with MCPBA, which is this guy here, and the pi bond opens up and forms a bond with oxygen. This creates an epoxide. How does the methyl group on propene influence the final epoxide structure? Take a few moments to think about this one. Since the reaction is stereospecific, the methyl group's position relative to the newly formed epoxide ring will remain unchanged. Nothing's going to happen. Trick question. As you prepare for the MCAT, keep in mind that each reaction is a story of change, stability, and molecular dance steps. You've just learned how to dance with alkenes, which is very, very important for the Chem Phys section of the MCAT. Thank you so much for watching our video on the detailed mechanisms of alkene reactions, and I will see you next time.